The question asks, how many of these molecules are polar? In order to determine how many of these molecules are polar, we must first draw the Lewis structures for each of these molecules, and then find the partial charges and their bond dipoles, and then find the net molecular dipole. Let's begin with SO3. SO3 has 24 valence electrons. Sulfur is the central atom of the Lewis structure, and the oxygen atoms form a bond with the central sulfur atom. This uses 6 electrons, so 24 minus 6 is 18. Now we must place the electrons on the outside atoms first to fulfill the octet rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Since sulfur and oxygen both have a valence of 6 electrons, 2 electrons from each oxygen atom can make another bond with the sulfur atom. This results in a Lewis structure where sulfur has double bonds with each oxygen atom. This is the Lewis structure for SO3. Now we must find the partial charges for this molecule. Since oxygen has a higher electronegativity than sulfur, the oxygen atoms will have a negative partial charge, while the sulfur atom will have a positive partial charge. This will help us determine the bond dipoles for this molecule. Based on the partial charges, the bond dipole will go towards the negative partially charged oxygen atoms. Now we must find out the net molecular dipole for this molecule. But in order to find out the net molecular dipole, we must first know the molecular geometry of this molecule. The molecular geometry for this molecule is trigonal planar because the molecule, the sulfur atom, makes double bonds with each oxygen atom, which means that this molecule has a domain electron geometry of trigonal planar because the central sulfur atom has no unpaired electrons. This also means that the electrons are distributed equally and the bond dipoles are equal throughout this molecule. Now I will draw the molecular geometry of SO3. Since SO3 has a molecular geometry of trigonal planar, the 3 outside oxygen atoms are apart by 120 degrees. This also means that the bond dipoles are 120 degrees apart. Therefore, since all 3 are equal bond dipoles, they cancel out, resulting in a net molecular bond dipole. of 0. Since the net molecular bond dipole is 0, this molecule, SO3, is nonpolar. Now, let's do the Lewis structure for OF2. OF2 has a valence of 20 electrons. Oxygen is the central atom for this Lewis structure with 2 fluorine atoms on the outside. Oxygen makes 1 bond with each fluorine atoms. Therefore, 20 minus 4, you get 16 electrons left over, which we now place on the outside atoms first, fulfilling the octet rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we subtract 12 and we get 4 left over. These 4 must now be placed on the central oxygen atom. 1, 2, 3, 4. This is the Lewis structure for OF2. Now, based on this Lewis structure, we can now determine the partial charges for this molecule. Since fluorine is the most electronegative atom on the periodic table, the fluorine atoms in this molecule will have a partial negative charge, while the oxygen atom will have a partial positive charge. Therefore, the bond dipole movement will be towards the fluorine atoms. Now we must find out the net molecular dipole for this molecule. But in order to find this, we must first determine the molecular geometry of this molecule. The molecular geometry for this molecule is bent because the electron domain geometry for this molecule is tetrahedral, because the oxygen atom makes 1 bond with each fluorine atom, therefore 1, 2 domains, but it also has 2 pairs of unpaired electrons, which means that this molecule has 4 domains. Therefore, it has a domain electron geometry of tetrahedral, and therefore the molecular geometry is bent. Since this is a picture of the molecular geometry for this molecule. Now we place the bond dipoles on this figure. The bond dipoles are moving away from the oxygen towards the negatively charged fluorine atoms. Since this molecule has a molecular geometry of bent, the net molecular dipole movement is going downwards and does not cancel out because it has 2 pairs of unpaired electrons. Which is why OF2 is polar. Now we will draw the Lewis structure for beryllium dichloride, or BeCl2. BeCl2. Okay, so there's 2 valence electrons from beryllium, plus 7 for each of the chlorine atoms, which is a total of 14, which gives us 16 valence electrons. The beryllium atom will be the central atom in this Lewis structure. And it will create one bond with each of the chlorine atoms. So 16 minus 4 will give us 12. And now we place the leftover electrons on the outside atoms, fulfilling the octet rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the Lewis structure for beryllium dichloride, or BeCl2. Now we must determine the partial charges. Since chlorine has a higher electronegativity than beryllium, the chlorine atoms in this Lewis structure will have a partial negative charge, while the beryllium will have a partial positive charge. Based on the partial charges, the net dipole is towards the chlorine atoms. Now we must determine the net molecular dipole. But before that, we must find out the molecular geometry of this molecule. The molecular geometry for this molecule is linear because the beryllium central atom makes one bond with each of the chlorine atoms. Therefore, this molecule has a domain electron geometry that is linear because it has 1, 2 domains, and there are no unpaired electrons, which is why the molecular geometry is also linear. So the molecular geometry looks just like the Lewis structure. If we place the bond dipoles, they cancel out, which creates a net molecular dipole of 0. Since this molecule has a net molecular dipole of 0, we now know that this molecule is non-polar. Now let us draw the Lewis structure for carbon tetrachloride, or CCl4. Carbon tetrachloride has, since carbon has 4 valence electrons, and each chlorine atom has 7, so 4 times 7 is 28. 28 plus 4 equals 32. This molecule has 32 valence electrons. Carbon is the central atom for this Lewis structure, and it makes a bond with a chlorine atom. So it makes 4 bonds, and each bond uses 2 electrons. Therefore, 32 minus 8 equals 24. Now we place electrons on the outside atoms, fulfilling the octet rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. This is the Lewis structure for carbon tetrachloride. Now we must find the partial charges for this molecule. Since chlorine has a higher electronegativity than carbon, the chlorine atoms will have a negative partial charge, while the carbon central atom will have a partial positive charge. Now we must find out the bond dipoles for this molecule. Since the chlorine atoms have a negative partial charge, the bond dipoles are towards the chlorine atoms. Now we must determine the net molecular dipole, but in order to determine this, we must first understand the molecular geometry of this molecule. The molecular geometry of this molecule is tetrahedral because it is the same as the domain electron geometry of this molecule, because carbon makes 4 bonds, each with a chlorine atom. Therefore, this molecule has 4 electron domains and has 0 unpaired electrons. Therefore, the molecular geometry for this molecule is tetrahedral, with carbon in the center. CO, each with 6 electrons. Now we place the bond dipoles, and since there are no unpaired electrons, the bond dipoles for this molecule cancel out, which makes this molecule have a net molecular dipole of 0, and this means that the molecule carbon tetrachloride is nonpolar. Now we draw the Lewis structure for O3. O3 has a valence of 18. Since they are all oxygen atoms, there will be 1 oxygen atom in the center with 2 on the sides. Which will use up 4 electrons, which gives us 14 left over. Now we must place the leftover electrons first on the outside atoms to fulfill the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry, that was a mistake. Let's start over. So the oxygen makes a bond with each of the outside oxygen atoms, which uses up 2 times 2, 4 electrons, which we have left over 14. So we place them first on the outside atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This leaves us with 2 more electrons, which we now must place on the central atom. 1 and 2. In this Lewis structure, the oxygen atoms the oxygen atom on this side can create another bond with the central oxygen atom. But this is also possible. This can also be drawn the other way around. Since this Lewis structure can be drawn in two ways, and they're both equivalent to each other. This will create a resonance hybrid, which means that the oxygen will share a bond continuously. Creating this Lewis structure, because this is a resonance hybrid Lewis structure. Based on this resonance hybrid, the outer oxygen atoms have a partial negative charge, while the central oxygen atom has a partial positive charge. Now we must place the bond dipoles for this molecule. The bond dipoles go towards the partially negatively charged atoms. Now we must find out the net molecular dipole for this molecule. But in order to find that, we must understand the molecular geometry. Since this is a resonance Lewis hybrid, we can still use one of these to find out the molecular geometry. Because whether the oxygen atom makes a double bond with the outside oxygen or a single bond, it still counts as one domain. So the molecular geometry for O3 is the molecular geometry is bent because the domain electron geometry for this molecule is bent also because there is one pair of unpaired electrons on the central oxygen atom. Therefore, when we draw the molecular geometry for this atom, the central oxygen has a pair of unpaired electrons, which means when I place the bond dipoles, they do not cancel out. And this creates a net molecular dipole that goes downwards, which means that this molecule, O3, or trioxide, is polar because it has one pair of unpaired electrons. Now we can go back and check off the molecules that are polar. So based on the Lewis structure and the net molecular dipole of each of these molecules, we now know that O3 is polar, CCl or carbon tetrachloride is nonpolar, beryllium dichloride is nonpolar, oxygen difluoride is polar, so check, and sulfur trioxide is nonpolar. So the answer to how many of these molecules are polar? Only 2 of them. Oxygen trifluoride and trioxide.